Aniruddhan,
Yes.
I'm not very happy with the inverter because you
Okay.
have VDD and then it's going in a.
That is
No?
true. That is true. Shall we refresh?
Is there a way to get a better one?
Okay. So we'll refresh
Yeah,
the student's memory. So I think you are referring to this inverter,
correct.
right?
Yeah,
So the curve looked something like this. So when we plotted VO versus VI,
yeah,
till VT there was no current.
correct.
This part looked nice, flat, but then you got something like this, no?
Yeah.
Something like this. Huh?
The
And I think at
output low side is not really nice.
it doesn't look
Something symmetric would be.
correct. So something like this it looked, no?
Yeah,
Something like
yeah.
this. Correct. You wanted something to look better like an inverter.
Yeah, it should be symmetric.
Correct. So in fact, so let me draw like this. In digital circuits, this is the inverter,
Correct.
right? So if you give input and output, so the way I'm imagining, you give 0, you need to get 1. You give 1, you need to get 0,
Yeah,
right? Or if I were to imagine 0 means ground and 1 means VDD,
yeah.
right? This is what we want.
Ideally, if I give something above VDD by 2, output
Correct.
should be low
That is correct.
and vice versa.
Correct. So what you are saying, if I were to draw the curve for this inverter here, so when you give 0, you want 1. So input is 0, you got 1, right? So you wanted here and here you want 0,
Correct.
not some VDD minus
Correct.
IDRD, right?
Correct.
So correct. So those 2 points are already, this point is okay, but the second point is a problem.
Yeah,
Correct. Second thing, most likely instead of giving ground, if I gave 100 millivolts or 200 millivolts,
Yeah.
it is still not VDD.
Yeah.
So let us say VDD was some 5 volts or something.
correct.
You still wanted to identify it as
Yeah,
a 0.
maybe something like up to 2.5, you should consider it as a low.
Correct. I understand. So you wanted perfectly symmetric.
Yeah,
So if this was VDD by 2, you actually want a curve that is like this almost.
Yeah.
Correct?
Yeah.
Ideally you want this.
Correct.
Symmetric.
correct.
Right? 0 to VDD by 2, you want VDD. VDD by 2 to VDD, you want 0.
Correct.
We need to build a circuit that does this.
What to do? Maybe the circuit also have to be symmetric.
Has to be symmetric, correct? Circuit has to be symmetric. Also, one thing I noticed, see the first part looks okay,
Yeah,
right?
that we can retain.
That we can retain. That is coming from the NMOS.
Yeah.
The problem comes coming from the resistor,
Oh,
right? So the output started reducing like this because VDD minus IDRD.
correct.
So we need to fix that part. We'll get rid of that part.
Okay.
We'll start by getting rid of that part and see what we can do. And like you said, symmetry, right?
Yeah.
So now, so we will retain this part, VI, get rid of the resistor, but you know, you still need some current to flow.
Correct.
You need something
So
on
there
top.
should be something.
Correct. So
Not a resistor. That's
not
clear.
a resistor. All the circuits that we have seen, we use transistors or resistors, right? And capacitors, but capacitor is not going to be very useful here.
Yeah.
You want DC current to flow.
Correct.
The only thing that you can do is use another transistor, right?
Oh. How?
Correct.
Which one?
Correct. So now we need to see which one. So see, we can't use a BJT suddenly,
Correct.
right? We want to build it
Yeah.
with MOSFETs.
One more NMOS, will it help?
One more NMOS, will it help? No, it won't, no, because it won't be symmetric.
Yeah.
It won't be symmetric because you have the source on the bottom,
Correct.
drain on the top. That won't help.
So it has to be a PMOS.
PMOS.
Oh.
I think it will have to be a PMOS.
We will try.
And we learned how to draw PMOS circuits, no?
Correct.
We will just reflect the same
Correct.
thing above.
Correct.
Because PMOS means source has to be highest
Yeah.
potential.
Yeah.
So we'll draw a PMOS transistor here,
Yeah.
like this. Okay. Now NMOS source was connected to ground. We saw that PMOS means source has to be connected to VDD. So we'll connect VDD here. NMOS drain was connected to output.
Yeah.
So we'll connect the PMOS drain to the output. And we saw that the input output characteristic of the NMOS and PMOS was almost the same.
Correct.
Same square law dependence.
Yeah.
So what we'll do, we will connect the two inputs also together.
Okay.
Right? This will hopefully give us a symmetric.
Looks symmetric.
Looks symmetric. Looks nice and symmetric.
Yeah.
So I think, like you pointed out, we have started from some very simple characteristics that we want. We notice the symmetry. We think that replacing the resistor with a PMOS transistor might help. And we have drawn some circuit. We'll take a look at this. So, so we'll take this circuit. So one NMOS, one PMOS, and we will change the input from 0 to VDD. We'll see what happens to the output. Okay. We'll start from Vi equal to 0.
Yeah.
We already said that nothing should happen till Vt.
It will be off.
It will be off.
That means.
So we'll call this M1 and M2.
Yeah.
So till Vi hits the threshold. Now we need to call this. So we'll call this Vtn.
The threshold voltage.
The threshold voltage. And we'll call this Vtp.
Yes.
And most likely this will have some Kn. This will have some Kp.
Yeah.
Right? So we'll need these two, I think. Because mu p is different, W over L of the PMOS may be different, and so on.
Definitely mu p is different.
Definitely mu p is different, right? Okay.
So
till Vtn,
the bottom M1 is off.
M1 is off, right? So this is Vtn. So we'll say this is VDD. So till here, M1 is off, no current. That means M2 should also be no current, no? We don't know whether it's off.
No current is
no
true.
Current is true.
Yeah, because
Correct?
the bottom is open.
Bottom is open. So no current. Now what will VO be? Earlier we had the resistance, it was VDD. Now we don't know whether it is VDD, no? We'll have to find out. So question is, we'll need to find out what M2 is doing.
M2.
Okay. So we'll write the state here.
Yeah.
When it goes from 0 to Vtn, M1 is off, no?
Yeah.
But M2, no? VSG, actually it is very large.
Correct.
Right?
Compared to VDSAT.
Compared to VDSAT. Right? So, and there is no current. Right? VSG is very large. So maybe what I will do.
Saturation. No?
It's in, well, we'll see. We'll see. So what I'm going to do, I'm going to on the next page, I'm going to plot the ID versus VSD for the PMOS transistor for M2.
Yeah.
That will, I think, help us understand. And we know, no, we have several curves.
Yeah.
We'll have several curves for the MOSFET. So this is a small VSG, slightly larger VSG, slightly larger VSG, and so on, right? And what we are saying is,
VSG is small.
VSG is very large.
Very large.
VSG, so you are probably here.
VDD almost.
VDD almost, right? It's almost VDD, but the current is 0, right? Clearly this is going to, we are expecting to have some current, no?
Yeah.
The only possibility for current to be 0 is you have to follow the curve till this point. That is the only possibility. If you are applying VSG, right? If you, in the saturation,
Correct.
right? Your current equation for the PMOS was half Kp the whole square.
Yeah.
If you apply VSG, current will flow. It cannot be in saturation, right? So the only possibility is the linear region.
Yes. Correct.
So this is Kp into VSG minus VTP into VSD minus VSD squared by 2. In fact, we know the current is 0. Only possibility is VSD is 0. Right? So that is the only possibility.
Oh, so that means it will be VDD itself.
Correct. That means that it has to be VDD. So until the NMOS is off, the output has to be at VDD. So our initial thought process that it is flat is correct. And we will mark the operation of the device, no?
Yeah.
So that is important to note.
Yeah.
So I'll say that NMOS off and the PMOS is in triode.
Yeah.
Or linear, I'll say. Very good. Till VTN, NMOS is off, PMOS has a very large VSG, but current is 0, so it has to be in the linear region. Okay, so we will mark that also here. So one portion of the curve we have got. It is going to be perfectly flat. So that we have got, no?
Yeah.
So first part looks good.
Correct.
After that, what happens? Current can flow.
Yeah.
Right?
Beyond VTN.
Beyond VTN, correct?
M1 will
start conducting. Current can flow, right? But we need to find out whether M1 is in saturation, M2 is in saturation or triode or what it is. My gut feeling is that because you're going to start from here, no?
Yeah.
At that point, most likely PMOS will continue to be in linear.
Yeah.
Because the output voltage is still going to be very close to VDD, right? M1 will have a large,
VDS is large, yeah.
VDS is large, which means that, and VGS is very small.
Correct.
It is just higher than VTN.
Yeah.
So most likely, NMOS will be in saturation, PMOS will continue to be in linear.
Yeah.
So
linear means it's like a resistor.
It's like a resistor, correct.
So it will start.
It will start going
down.
Going down, correct.
As you increase VI.
As you increase VI. And also the current keeps increasing because the NMOS current is quadratically related to the input voltage and it is in saturation.
Correct.
So it will increase, current will increase, so output will drop non-linearly. M1 is in saturation, M2 is in linear. So maybe now is a good time to color code. What I will do, I will color code in this color. Then the next one I'll color code in a different color. Shall I use red?
Yeah.
Okay. So now we'll draw I'll draw the curve in black, but we will color code in red, the marking. Yeah. So VI greater than VTN, slightly greater than VTN. So now the voltage has to start falling because current is flowing.
Correct.
So now what that means is the PMOS will start moving along this curve.
Yeah.
It is still in linear, but it is moving for larger VSD, right? So that we will show by reducing something like this. It will do, right?
After some time, M2.
After some time, if you increase a little bit further, M2 can go into saturation because now the output voltage is dropping.
Correct.
So this voltage is dropping. The drain voltage of M2 is dropping.
Yeah.
The source voltage is constant at VDD.
Correct.
So eventually it will move into the saturation region. That is this part, no? This part of the curve is saturation. So eventually the PMOS can move into saturation.
Yeah. It may not come to VDD level.
It will not come to VDD level. Correct. So in fact, this is also dropping. It is moving down the curve.
Correct.
Because VI is also reducing. Correct. So it is not moving along the same curve.
Yeah.
It is moving across multiple curves, some other curve, multiple curves it is doing because VI is increasing.
Yeah.
So what we'll do, we'll mark this as
M1 saturation.
correct. So
M2 linear.
NMOS saturation, PMOS linear. And like you said, so that is this point.
Yeah.
And at some point, like you said, voltage goes low enough such that PMOS goes into saturation.
So both are in saturation.
Both are in saturation. Okay. So you can get these curves, by the way, by solving the equations.
Yeah, but we want to get an
We
overall
want to get
feeling.
an overall
Yeah,
feeling.
yeah.
Right. So now that curve, NMOS is in saturation, PMOS is in saturation. The NMOS current is related to VI. The PMOS current is related to VDD minus VI.
Yeah.
So it can happen only at one value of VI.
Correct.
Right?
Yeah.
So because it's a pure quadratic, no dependence on VSD at all. So there has to be only one value of VI for which that will happen. The two currents will be exactly equal. So in fact that means that this will be a straight line like this, no? So it can only happen at one value. So we'll call that some, I'm going to call this some VTH, okay? Some VTH, we'll just call it some VTH.
Oh.
That is the threshold of the inverter. In some sense, it is going from high to low.
So now VDS of the M1 is reducing.
VDS of M1 is reducing because now it's falling very fast.
Correct.
Right? So the current is increasing. The VSD is increasing for the PMOS, VDS is decreasing for the NMOS.
So which means M1 will enter into.
Correct. M1 will enter into
Triode
triode.
region.
Correct. So we'll write that here.
Yeah.
So VI equal to VTH. So that is the previous case. I'll just use a different color, maybe this color. Yeah. I'll use this color.
Yeah.
Okay.
Yeah.
And we'll also mark that here.
Yeah.
Both are in sat. And like you said, now one of them will enter into the linear region. So I will show the curve like this. So now again it will do something like this, no? So it will do something like that.
Because M1 is in triode and the other one is
Correct.
continuing in
saturation. Correct. So in this case, the PMOS will be in saturation, the NMOS will enter the triode region.
Yeah.
Correct. So M1 will be in linear and M2, which is the PMOS, in sat.
Yeah.
And that is this curve here.
Yeah.
And we can imagine now that it is symmetric. At some point of time, till that will continue till the PMOS turns off. Now we wanted the symmetric circuit, symmetric. Now we can take a guess.
Because VI is keep on increasing.
Correct.
At some point, VD minus VI will become smaller than
VTP. Correct. And that will happen at, so I'll show it like this. Something like this. It will happen at VDD minus VTP.
Yeah.
Right?
This will be like the top one.
It will be like the top one. So I should draw it better, no? Something like this?
Yeah. Yeah, yeah.
Is better?
Yeah, perfect.
Correct. Yeah, I think I drew it too shallow.
Yeah.
Correct. And this is the region where NMOS linear and PMOS is in sat.
Yeah.
And finally, you have the last region, right? Which will just be till VDD.
PMOS is off.
PMOS is off. So which color shall we use? I'll use one of this color. Now in this case, NMOS has to be linear.
Yeah.
Because the output voltage has fallen to 0, right? So the NMOS will be in linear region by definition. So that is, we'll show that here. So VI greater than VDD minus VTP.
Yeah.
right? So your M1 linear, M2 off, right? Okay, good.
Oh.
This looks much better, no?
Yes, yes. This is very clean
Correct.
inverter.
Very clean inverter, very clean symmetric. We wanted like a nice
Yeah.
flat one.
Yeah. But it's okay.
It's okay. We are getting very close to it.
Correct. Correct.
Right? We're getting
We
very,
should not be so greedy.
we should not be so greedy. Agreed. Correct.
So now there is no resistor actually.
Yes, that's true. There is no resistor. It is full of transistors only. Correct. And we can set based on the width of the device, VT of the device, we can set VTH to VDD by 2. Right? You can set.
Okay.
In fact, you can set it something else also.
Correct.
Right?
But VDD by 2 may be the best.
Maybe the best.
Mostly.
You want a symmetric
Correct,
inverter,
correct,
you want VDD by 2.
So you have P and N.
Correct. So NMOS, PMOS inverter.
No,
Shall we
better
call it?
name.
Better name.
Yeah.
We want a better name.
Yeah.
Okay. So
You have something.
yeah, we have both N and
Yeah,
P, no?
yeah.
N type and P type.
Correct.
So the word I think we should use is complementary.
Exactly.
Right? That is the word you are looking for?
Yes.
Correct. Complementary MOS, right? Or CMOS,
CMOS.
is the word that is most commonly used, right? So this is a CMOS inverter. So I'll write that here. So I'll move that here. So that is the what this circuit would be called, a CMOS inverter. In fact, people might have heard the word CMOS.
Correct.
Who knows? I mean, nowadays you hear a lot, no, about semiconductors, microchips, and so on. They might have actually heard of the word CMOS.
So we discuss about the ECL family.
Correct.
So CMOS is another family.
CMOS is another logic family. Correct. So you can also have a CMOS logic family. Correct. So the ECL logic family is very good for high speed. CMOS is very good for low power.
Yeah.
Right?
Because there is no resistor, I can say.
There is no resistor. In fact, if you look at the inverter that we wanted to build, you are going to give 0 or 1 at the input. In fact, when you give 0 or 1, the nice thing about this circuit, no?
One of this is off.
One of these is off.
No current.
No current, right? So either of these two states, there is no current. So it is a very low power family.
Oh. So only when there is a transition, it draws some current.
That is correct. Only when you switch from 0 to 1 or 1 to 0, you will draw current.
Oh, that's cool.
Correct. Correct. So this would be this is a very common low power logic family. In fact, a lot of modern electronics, processors, things like that use CMOS logic.
Great.
Yeah. So this is in fact a very important logic family from that point of view.